So welcome back on STEM Baba. We were discussing the chapter 9, which is the linear momentum and collision, and we have discussed 4 topics up till now. And the first topic we discussed was momentum, then हमने पढ़ा था momentum and the second law, then impulse, and in the last video we discussed about the conservation of linear momentum. So today we'll see some examples on this topic, conservation of linear momentum, and then we'll start the fresh topic, collisions. So बिना किसी देरी की शुरुआत करते हैं इस शानदार वीडियो। So there's a first example, and it says that two groups of canoeists meet in the middle of the lake, that you can see here. And after some period, what happens that the person in this canoe 1, he pushes on the canoe 2, that you can see here, with the force of magnitude 46 Newton. And due to the Newton's third law, the action is equals to reaction. So this force would be acting on this person sitting in the canoe 1. Now we have to assume that the mass of the canoe 1 and its occupant is 130 kg. Canoe is basically what? Now ko bol rahe hain canoe. And so let it be m1. Now the mass of the canoe 2, this is the total mass of the canoe 2 and its occupant. जितने लोग यहाँ बैठे हैं, जितना now दोनों का mass मिला के we have to take it to be 250 kg. And we need to find the momentum of each canoe after 1.2 second of pushing. So when delta t is 1.20, then at this instant, what would be the momentum of each canoe? Now there are two approaches in this question that we need that we can take. The first approach is first find the velocity of the canoe 1 and 2 after this much of time, 1.2 seconds, and then just multiply it with mass, because we know that the momentum is what? Mass into velocity. This is what we define as momentum. Other way around, we can use that the rate of change of momentum is what? The force applied on the net force applied on the object. So two approaches are there. First, we're going to solve this step by step by using the first approach, and then we'll see by the second approach. The answer will be same in both the case. Okay, so the first way. Now, if we consider the canoe 1, this canoe 1. So we have, by using the Newton's second law of motion, we can write that the acceleration for the canoe 1, this will be equals to the net force on the canoe 1 divided by the mass. Now this force is in the negative x-axis, and this direction we have taken positive x. So force we can write minus 46 divided by the mass for canoe 1 is 130 kg. So the acceleration will be minus 0.35 meter per second squared. So this would be the acceleration. Now what would be the acceleration for this canoe 2? So this would be sigma F2 divided by mass, right? F2, the force is same, but it is along the positive x. So 40, this time will take positive sign, divided by the mass. This time is 250 kg. So this is 0.018 meter per second squared. We need to find the velocity at after this much of time period. So we can use the equations, kinematic equation that we studied earlier. V equals to u plus at. Initial velocity it was 0. So the velocity for canoe 1, this would be acceleration. This is the acceleration multiplied with delta t. So this value multiplied with 1.20, you will get this value to be negative 0.42 meter per second squared. Similarly for canoe 2, the velocity will be 0.22 meter per second squared. Now we can easily find the momentum for canoe 1 and canoe 2 easily. So the momentum for canoe 1, this will be, and this is along the x direction, so p1x I can write. So this would be the mass of canoe 1 multiplied with the velocity for the canoe 1. So the mass we have 130 kg. 130 multiplied with v1 we have minus 0.42, and that will be equals to minus 55 kg meter per second. and if you find the momentum for the second canoe, मतलब दूसरे नाव का अगर मैं momentum निकालूं तो m2 times v2, this will be equals to m2 we have 250 multiplied with v2 we have 0.22 meter per second, and that will also be equals to this value. The magnitude would be same, but the sign will be positive this time. 55 kg meter per second. And if you see the sum of momenta of these two moving canoe, this will be equals to 0. The total momentum, this will be this value plus this would become 0. Correct? And why this total momentum is 0? Because initially the momentum for these two canoe was 0. Initially they were at rest, and after this person pushes on the canoe 2, if we are taking this as our system, then this force will become the internal force, and if you use that the Newton's second law of motion, that is the net forces is equal to the rate of change of momentum, and since there is no net force on the system because these are the internal forces which will cancel each other, so here the change in momentum will be equals to 0. So initial momentum was 0, and final momentum, total momentum is also 0, and that is why the change in momentum is also 0. So I hope you got the problem. And second method was this only. This was the second method. If we take the second method, the momentum will be, for if you consider the second canoe, this would be the force multiplied with delta t. So force we have 46 Newton. So 46 multiplied with 1.2, which is nearly the same value, 55. And for canoe 1, this would be this time minus 46 we have to take because the direction is along the negative x, multiplied with delta t, and that is minus 55. And here also the total momentum is 0, which is the same value. So you can solve this question by any of these two methods. You'll get the same answer. The reason behind it, by solving these by using this kinematic equation, is just to show that here momentum is conserved, but not the velocity. Velocity is different here. Here the velocity is minus 0.42, and here the velocity is 0.22. The velocity is not conserved, but the product of mass multiplied with velocity, that is the momentum, this is conserved after and before the collision. So I hope you got the problem. Now one question I'm giving to you. Here in this example we see that the momentum is conserved, but is the kinetic energy of the system is greater than, less than, or equal to the initial kinetic energy? Means what I'm saying is, when they were at rest, they have some kinetic energy which is 0. At rest the kinetic energy would be 0, but after pushing it and time delta t, after this much of time, will the kinetic energy of the system be equals to 0 or greater than or less than the initial kinetic energy? This is what we have to find. So pause the video and try to think that is the kinetic, what would be the final kinetic energy after 1.20 seconds. So I hope you tried. Now it's pretty simple. Kinetic energy, we know that it is basically half mv square. We don't have to take the direction. So in both the case, we see that here the velocity is negative and here the velocity is positive, but when you square it, the kinetic energy will be positive. So it doesn't matter in which direction the canoe is moving, the kinetic energy would be positive. That is why the final kinetic energy of the system, that is both the canoe, will be greater than the initial kinetic energy. This is what we can conclude. Now let's take one more example. Now this is the next example, and here we have this lumberjack that has the mass of 61 kgs, and he is standing on this log who is pointing towards the shore, and this is the direction, positive x, that we are taking. Now the mass for the log is given to be 320 kgs, so ml. This is 320 kgs. So let this be mlj, because this is lumberjack, so that we don't have any confusion. So mlj I'm taking, and here this is the mass of the log. Okay. Now initially the system is at rest, the log and the lumberjack is at the rest. Now what happens, the lumberjack starts running or starts moving with a speed of v relative to the log. Now we need to find that is the speed of the log relative to the shore greater than, less than or equals to v. तो देखो यार सिंपल है चीज, we have to use the conservation of momentum here, because if you take this to be as our system, this whole, the log and the lumberjack to be our system, the force the lumberjack applying on the log is internal force, and since there is no external force acting on the system, so we can conserve the momentum. So the final momentum, it should be equals to the initial momentum, and initially the momentum was 0, so final momentum should also be equals to 0, correct? Now final momentum means the momentum of the log plus the momentum of the lumberjack. So mlj times v plus the mass of the log is ml times v, it should be equals to 0. Now this is vl we can write, and this is lj I can write. Now since if you rearrange these terms, you will get mlj times vlj is equals to negative of ml times vl. Now since here we see that the product of these two numbers should be equal, if we just consider the magnitude, then we can say that here the mass of this lumberjack is less and here the mass of log is more. So to balance these two terms, this should be less and this should be more, correct? That means what I'm saying, that the velocity of the lumberjack should be less than this velocity, which is 1.8. So this VL will be less than VLJ, that is the velocity of the lumberjack. You can prove it here by just plugging the values here. So if MLJ, this is 61 kg, VLJ is 1.8 meter per second is equals to negative of ml, we have 320 times vl, and if you solve it for vl from here, you'll get vl to be equals to negative 0.34 meter per second. Here what this negative sign signifies, that the direction for the direction of the log relative to the shore is in along the negative x. So if you see just the magnitude, this value is less. This is what we have to, this is what we concluded there, and here we have proved it mathematically. So we can say that the in vector terms I can write that velocity of the log, this would be minus 0.34 meter per second x cap, correct? So this is all with the examples of conservation of linear momentum. Now I'll be giving you one practice question. So let's take the practice question first. So here we have this. This is some, you can take it as a bomb or something like that. So this is a bomb, and initially the bomb is at rest. And what happens? The bomb is exploded into two parts, part 1 and part 2. This is part 1. And this is part 2. Now after explosion, piece 1 has kinetic energy twice as of piece 2. That means if this piece has kinetic energy K, then this piece will have the kinetic energy 2K. Next it says that if the piece 1 has a momentum of magnitude P, then what would be the momentum for the piece 2? Further, if the mass of this piece is m, then what would be the mass of this? This thing is given. We have to calculate that what would be the momentum. If this is p, then what would be p? What would be the momentum in terms of this p, and then what would be the mass? One hint I'm giving. Since if you take this as our system, then we can say that the bomb basically which is exploded, it has no external forces, so the momentum would be conserved. And by using the conservation of momentum, we can tell that what would be the momentum of this second piece, and also what would be the mass by using the energy and momentum. So this is the hint I've given. Now this is all about the conservation of momentum. अब हम discuss करने जा रहे हैं collision. So let's start the new topic, collision. So collisions. So first of all, understand what do you mean by the term collision in physics. So whenever two objects collide with each other such that the external force on the system is either zero or negligibly small, then we say that it is a collision. For example, रेल के डब्बे हैं, ये कुछ स्पीड v से जा रहा था और ये कुछ स्पीड v/2 से जा रहा था. तो कुछ टाइम बाद दिस ब्लॉक और दिस रेल का डब्बा will collide with this one, and this is what we call the collision. Now here you must understand that the net force acting on these two blocks is zero if we consider this to be as our system. क्योंकि देखो यहाँ पे क्या है, weight is acting in the downward direction which is balanced by the normal force, because अगर मैं ये surface पे देखूँ, किसी surface पे चल रहे होंगे ना भाई ये blocks, so normal force is balanced by the weight, and drag force हम लोग consider नहीं कर रहे, it's a very negligible kind of force. So here the net force is zero, that means the collision has occurred. Another example we have of a person hitting a ball by using his bat. This is also a collision. Now here you might have a confusion that when the ball was coming here like this, the gravity force was acting on this ball. There is some net external force acting on the ball. So how can we say that it is a collision? Because this mg force is very less as compared to the force when these two objects are interacted. And हमने ये example discuss किया था कि ये पिछले ही वीडियो में मैंने बताया था कि when these two objects interact, the ball and the bat, the internal force between these two objects is near about 11,000. ये example हमने discuss किया था in the last video. And if you take this gravity force mg, this is far less than this value, so we can neglect it, approximate it to zero as compared to this. So we can consider this to be a collision. Now you know what is fascinating about collisions? The thing is that during collision the momentum of the system is always remains conserved, but the kinetic energy may be conserved or may not be conserved. That is why we have made two categories of collision. The first one is inelastic collision and the next one is the elastic collision. So whenever the kinetic energy is conserved of the kinetic energy of the system is conserved, then we say that it is an elastic collision. And whenever the kinetic energy is not conserved, we say it is an elastic collision. This is the two categories we have made based on the kinetic energy. So finally I'm just concluding the things. So in inelastic collision, the momentum is conserved, that means the final momentum is equals to initial momentum, but the kinetic energy is not conserved. So final kinetic energy is not equals to the initial kinetic energy of the system. Now there is something called the completely inelastic collision. It's a special case of inelastic collision, and in completely inelastic collision the two objects stick together after the collision. So there is a new category which we call just a special case, not a category, it's just a special case of inelastic collision which we call the completely inelastic collision. So what do you mean by this? When the two objects stick together after collision, then we will say that it's a completely inelastic, because in this kind of collision the maximum amount of kinetic energy is lost. the maximum kinetic energy is lost in this kind of collision, in this type of collision. So this is lost. एंड फर्दर हम कह सकते हैं कि अगर अगर कंप्लीटली इनलास्टिक कोलिजन के केस में कि अगर टोटल मोमेंटम ज़ीरो है, दैट मीन्स कि जो काइनेटिक एनर्जी वो पूरी की पूरी लॉस्ट हो गई है. बट अगर टोटल मोमेंटम इज नॉन ज़ीरो, देन मतलब कुछ काइनेटिक एनर्जी बच गई है आफ्टर द कोलिजन. जैसे कि मैं बात करूं कि अपने पास ये दो ऑब्जेक्ट्स थे, करेक्ट, एंड आफ्टर कोलिजन दे बोथ ऑब्जेक्ट are in stick together, it just stick together. एंड अगर मैं इसका इनिशियल मोमेंटम देखूं और फाइनल मोमेंटम देखूं, अगर ये दोनों होंगे तो सेम, नो डाउट दोनों के मोमेंटम सेम होंगे, बट दोनों के मोमेंटम अगर 0-0 है नेट मोमेंटम, तो इसका मतलब ये है कि इसमें पूरी की पूरी काइनेटिक एनर्जी लॉस्ट हो गई है. आप ये कह सकते हो फॉर एग्जांपल कि आप ये ऑब्जेक्ट ऐसे जा रहा होगा, ये ऑब्जेक्ट इधर जा रहा होगा, तो इसका जो नेट मोमेंटम था वो ज़ीरो था, और स्टिक करने के बाद उसकी जो मोमेंटम है, नेट मोमेंटम फिर से ज़ीरो ही रहा. इसका मतलब कि जो पूरी की पूरी काइनेटिक एनर्जी, इसकी इनिशियल काइनेटिक एनर्जी थी, वो पूरी की पूरी ख़त्म हो गई है, ज़ीरो हो गई है. बट अगर if the total momentum is not zero, suppose यहाँ पे 3 kg मीटर पर सेकेंड है, यहाँ पे भी इतना ही होगा, नो डाउट 3 kg मीटर पर सेकेंड ही होगा, बट काइनेटिक एनर्जी लॉस्ट हुई होगी और काफ़ी ज़्यादा हुई होगी, बट ज़ीरो नहीं हुई होगी. जैसे पिछले केस में ज़ीरो हो गई थी ना, ज़ीरो नहीं हुई होगी, कुछ 10-15-20% बच गई होगी. एज जैसे डेटा हम दिया होगा उसके हिसाब से हम बता देंगे एग्जैक्टली कितना बचा होगा, लेकिन हाँ करीब इतनी ही वैल्यू बची होगी. So this is what we can say about the completely inelastic collision. Now let's discuss some mathematical equation that we see in this inelastic collisions. Now before discussing the mathematical equation, we have these two figures, and you have to identify that which of this example will be an inelastic case and which will be the elastic collision. So here if you consider this one, just first of all just pause the video and try to figure out on your own. Now I hope you tried, but let's discuss now. तो देखो यहाँ पे क्या हो रहा है कि इस केस में this will be a inelastic collision. and inelastic क्यों है ये? Because the maximum the initial kinetic energy of the system, basically these two players, is being lost in repositioning their masses and in breaking of this glass. So the kinetic energy is lost here, this is not conserved. That is why the collision is inelastic. But in this case, when the ball hit on the head of this player, the velocity with which it hits, it almost rebounds with the same velocity. That means the kinetic energy almost remains the same. So this will be a case of elastic collision. There is nothing called the perfect elastic. There is nothing called perfect elastic in nature. Just we can say that it is close to the elastic. So that is why we are calling it to be elastic collision. And this is with sure we can say that this will be the inelastic because the kinetic energy lost here. Still the momentum will still be the conserved, will still be the same. Now let's discuss some mathematical equations related to the inelastic collision. So we'll be discussing inelastic collision in 1 and 2 dimension. So first let's see in 1 dimension. Vertical tracks. So here we have these two trains of mass m1 and m2 running on the smooth vertical track with velocities v1 and v2. Now finally, when these two trains are coupled, they move with a common velocity vf. Correct. Now we need to find out what is the value of this final velocity. Now here we see, if we consider this to be as our system, we can say that the momentum remain conserved because there is no external force acting on it. So what we can write, that the final momentum will be equals to the initial momentum. So initial momentum we have for this two train blocks, we have this m1 v1 plus m2 v2, correct, and this direction we have taken positive x. Now the final momentum will be mass times velocity. So mass, now when they are coupled, when they are stick together, the mass would become m1 plus m2, and the common velocity they have vf. Now just equate these two things and we can write that vf will be equals to m1 v1 plus m2 v2 divided by, this would become m1 plus m2. So this is a generalized formula for calculating the final velocity when the two blocks are coupled, when they are attached, when they are stick together after the collision. Then this would be the expression. Now there are some special cases. Like here we have understood one thing, that the final velocity will be equals to the initial momentum divided by the total mass of the system. This is what we can say from here. Now, if the initial momentum was 0, then what we can conclude, that the final speed Vf, this will be equals to 0. And how come the initial momentum can be 0? It can be 0 if this train block is moving in this direction and this block is moving in this direction. And this momentum would be positive and this momentum would be negative. Then total can be 0 if their magnitudes are equal. Then this final speed or final velocity for the blocks or the train will be 0 after collision. Now what happens if they have initial the similar speed and same mass initially? So if mass and the velocities are equal, then what we can write, the final speed would be mass and v's value, so m times v plus, this is also same, m times v divided by m plus m would become 2m, because we have taken that masses are equal for both the blocks and they are moving with same speed, so that would be v over 2. So in this case, this is the second special case and this was the first special case. Here the final speed becomes half of the initial speed. So these were the two special cases. Now let's discuss the inelastic collision in 2 dimension. So in case of 2 dimension, what happens, that here we can consider this is positive x direction, this is positive y direction. Now this car was moving along the positive x and this car was moving along the positive y, and after collision they are moving in xy plane in 2 dimension. So this is the case of inelastic collision in 2 dimension. And since momentum is a vector quantity, so we can conserve momentum in x direction separately and the momentum in the y direction separately. So what we can write, that the momentum, initial momentum in the x direction, this will be equals to the final momentum of the system in the x direction. Similarly, the momentum in the y direction will be, the initial momentum will be equals to the final momentum in the y direction. So these two equations we can use to find the velocities, the final velocity and this relative angle theta relative to the x-axis. So this is all about the inelastic collision in 2 dimension and in 1 dimension. So next अगले वीडियो में हम लोग डिस्कस करेंगे कुछ एग्जांपल्स बेस्ड ऑन inelastic collisions, and then we'll start with a fresh topic, elastic collision, in the next video itself. So अभी इस वीडियो के लिए इतना ही. अपना बहुत ही ख्याल रखिएगा. Goodbye.